All right, today we are moving on to a somewhat, well, it's a new topic, but it's going to fit in with what we're doing currently. But maybe we'll take a day or two with this specifically, and that is summation notation, also known as sigma notation. So what we do, in math, we have these sequences, we have these, lists of numbers, and some of them have special properties and some cool things that happen to them. And what they did was they're like, oh, well, what happens if we add up all these numbers, right? Now, if we have a long, long list of numbers, it's really hard to write out, the sum of all that, right? To write out every single term and with a plus sign in between. So they decided that they'd use a quicker method using a symbol, okay? And that is the Greek symbol sigma, all right? That's all right. You may see it with little things there, okay? But that is sigma notation. Now, what that tells you is that you're going to be adding everything. So the way sigma notation works is a little different. There are a few parts. So here, if you see the sigma, that just means you're taking the sum. Now, whatever comes after the sigma is what you're taking the sum of. So what comes after the sigma changes depending on what we're looking at, okay? And I'll show you in a second. But this, right, with a sub I, that's telling me I'm adding up different terms of my sequence A, right? So I is called the index of summation. So most of these sigma, most of these summations will have I down here. They might have a different letter like K or J, but it's the index of summation. And you'll see that appear after the sum. Okay, and then there's going to be a number on top, and that's called the upper limit of summation. And that's telling us where we stop. Okay, and in this case, we have a 1 down here. 1 is the lower limit, and that tells us where we start. Usually it's 1, sometimes it's 0, and on a number of occasions, we might start at a number greater than 1. We might start at 2 or 3 or 4. Okay, so that's pretty, that's standard throughout all summation notation. What changes is what comes after the sigma. All right, so in this case, all right, again, like I said, this is telling me that I'm using some kind of sequence, and I'm adding the numbers from 1 to n. So that's telling me I'm doing A1 plus A2 plus A3, and I plug in all the numbers from 1 to n, and I add those up. All right, so if this was an 8, then I'd add up all the terms from the first term to the 8th term. All right, so, but sometimes we just plug in the numbers. All right, so let's take a look at an example or a couple examples. Kind of get you used to looking at this. Okay, so this one is where we're just going to do a kind of a normal sum. So this is the sum from 1 to 5 of 3i. So what this is telling me is I'm going to be adding all the terms where I plug in numbers from 1 to 5 into here. Right? So first I'm going to have 3 times 1. Right? That's the first one. Then I'm going to add to that 3 times the next number, which would be 2. And then I add to that 3 times 3. And then I add to that 3 times 4. And then I add to that 3 times 5. And that's where I'm going to stop, because this is telling me that my I goes from 1 to 5. And then after that, it's just, normal arithmetic. So I have 3 plus 6 plus 9 plus 12 plus 15. And we add up all those together. And that gets us 45. All right, so there, it's pretty straightforward. And any questions about, the basic summation notation? All right, let's take a look at another one. Slightly different, but same concept. I'll do sigma. I'm going to change it here a little bit. So now I want to find the sum from 3 to 6 of 1 plus k squared. All right, so the only there's two differences here. I'm using k instead of I, which, it's a variable. That doesn't really mean anything. But now I'm not starting at 1, I'm starting at 3. So this is telling me I'm plugging in the numbers from 3 to 6, so 3, 4, 5, 6. I'm plugging them into this formula, and then I'm adding all those separate answers up. All right, so, I can write it all out. So I'm going to have 1 plus my first term, 3 squared. And my second one is going to be 1 plus 4 squared. My third one is 1 plus 5 squared. And then I'm going to have 1 plus 6 squared. And that's where I'm going to end because that is my upper limit, 6. All right, and again, now we just do some basic math. 3 squared is 9, plus 1 is 10. 4 squared is 16, plus 1 is 17. 5 squared is 25, and 1 is 26. 6 squared is 36, plus 1 is 37. We add up all those together, and we get 90. So we can say that the sum from 3 to 6 of 1 plus k squared is equal to 90. Right, so it's a combination of, basic function stuff where you just plug in the numbers, and now we added the new concept of summing those numbers. All right, let's take a look at one more before we get to some properties and some rules. This one's a little interesting. So we are going to find the sum from 0. That's an I. Oops, went too far. So here we're going to find the sum from 0 to 8 of 1 over I factorial. So this is combining what we did yesterday with the factorial with what we're doing now with the sums. And actually this here is an interesting sum. Right, so we're going to do the same thing. We're just going to plug in the numbers. Right, so I'm going to write that out first. I'm going to just stick to black ink because it's a pain in the butt switching to red ink back and forth. So I'm going to have 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial. All right, so I have all of these all the way up to 8. All right, so my numerator doesn't change, that's always 1. So what I'm essentially doing is I'm adding smaller and smaller fractions. Now remember, 0 factorial is 1, so 1 over 1 is 1. Again, 1 over 1 is 1. 1/2, 1/6, 1/24. 5 factorial is 24 times 5, which is 120. 6 factorial is 120 times 6, which is 720. And then these are starting to get a little larger. 50, 40. And then 1 over 40,000. 320. All right, so we're going to keep them as fractions for now. But when we add them up, we get an interesting number. We get 2.71828. Now, it's been a minute, but you might be able to recognize this number. It is our exponential, right? Our e, which is the opposite of the natural logarithm, ln. Right? So back when we were doing exponential and logarithm problems, right? This is one of the ways that we get an approximation of e. Now, we can get real fancy. I'm not going to calculate this, or I'm not going to go over this right now because it's kind of outside of our pay grade. But there's something called an infinite sum, where we add up an infinite amount of terms. Now, normally, that kind of gets out of hand, right? If I was doing an infinite sum with something like in example 1 or 2, I wouldn't have an answer, right? Because I'd keep adding numbers, and those numbers would get larger and larger and larger and larger, and it would get out of hand, and there would be no answer. Okay, I can't keep adding numbers larger and have some single number answer. I wouldn't have 45. Okay, but when we're adding fractions together, it doesn't matter how large my fraction gets, because essentially what happens is the larger my fraction gets, I'm not really adding much to it, right? 1 over 40,000 as a decimal is 0.000025, right? So adding that to something like, 1 plus 1 isn't doing much. So if I added 9 factorial, that'd be an even smaller decimal, right? They're, 10 to the negative 6 or something like that. So there's some interesting stuff, and we might be able to get to it at the end of the at the end of the year. But there's some interesting stuff when we do summations with fractions. All right, so I just wanted to show you that. We get this exponential, the number e, from this sum. Okay, so now that we kind of know basically how they work, let's look at some of the properties. So the first property is if I am taking the sum of a constant number, well, then that's just going to be c times whatever my upper limit is. All right, and if we think about it, so let's say I did from 1 to 5 of 4. Well, this is telling me that I have 5 terms, but what I'm adding doesn't depend on what number those terms are. So my first term would be 4, my second term would be 4, right? And I do that 5 times. Right? So I just multiply whatever the n is times that constant. All right, so that's a pretty straightforward one. All right, so again, if you're just finding the sum of a constant, then you just multiply the upper limit times the constant. our second rule. Again, if C is a constant. All right, and we have that constant times terms. Well, then we can pull that constant out and just worry about the sum later. All right, we would calculate this, and then we'd multiply that by the constant. So we can pull that out. All right, and again, just to show you a quick example, we'll do something really light. So let's say so the sum from 1 to 3 of 2 times I plus 1. So what's telling me is I can pull that 2 out, and I just worry about the sum of I from 1 to 3 of I plus 1. So that gives me 2 times, well, I have 2 plus 3 plus 4. 2 plus 3 plus 4. 9. 9 times 2 is 18. All right, if I did it the long way, okay, I have 2 times 3 plus 2 times 4. I'm sorry, I forgot the 2 times 2. All right, so essentially what we're doing is we're factoring out that 2 from all of our terms. Okay, so we can pull out that 2. We can deal with the sum, and then we multiply by 2 at the end. Our third one is kind of familiar. So if I'm finding the sum of a sum of terms, I can break that up. Into a sum of sums. And the fourth one is the same, but with subtraction. I'm just going to move down a little bit so I can finish this. I equals 1 to n equals 1 to n. All right, so we have 4 basic properties of sums. And I think we'll stop there for today. Yeah, we only got 5 minutes left. Okay, so what this does, though, is this sets us up for the counterpart to sequences, and that is a series. Now, they are closely related because, and I'll expand on this more tomorrow, and we'll write it down for our notes. But a series is just the sum of a sequence. So if you take a sequence and you add up all the numbers, right, that's just called a series. All right, so that's what we'll pick up with tomorrow. All right. So just